Hello everyone, my name is Yuan. Now I work for Jaguar Microsystems, a new DPU startup. Today I'm going to introduce a new solution to support connection tracking in OVS and share the experience of how we tackle with the performance issue and hardware offload supporting. Firstly, I will give a general introduction about the community solution and show the challenge we are facing now. And then I will introduce our proposed solution and share the impact on software performance and hardware offloading support of the new design. Security group, in fact, is a must feature for most using scenario in cloud environment, and currently we rely on the CT action to support this feature. The left side picture shows a typical network topology. For the traffic in or out of the VM, it will go through multiple OpenFlow tables defined by the control plane, such as connection track, FTP, and as well as route table. And we do a packet trace in the TX direction, as shown in the right picture. From the tracing result, the packet gets recirculated when it goes through the connection tracking table. And Vexler decaf action will also trigger a recirculation, so the packet gets recirculated once in the TX direction and twice in the RX direction. In this talk, we will focus on how to tackle with the recirculation triggered by the CT action. For the newly received packet, the CT state will be initialized to untracked state, and thus it will match the first flow, and the packet will send to the connection tracking module during execute the CT action. The CT action forks the pipeline processing in two. The original instance of the packet will continue processing the current action list as an untracked packet. In most cases, there are no action after this. Thus, the original packet gets dropped, and the forked will be sent to the connection tracker, which will be re-injected into the OpenFlow pipeline to resume processing, with the CT state update to track and new, which will match the second flow. In a word, for each packet going through the connection tracking module, it will update the connection state while CT actions and recirculate back to match based on the new connection state to figure out what is the next station the packet needs to deal with. From the data plan point of view, the whole design is flow-oriented and stateless, which means it's hard to keep per connection status information inside a flow. Thus, to support connection tracking, create a new session table and maintain it inside the CT actions. Thus, the whole pipeline turns into doing the matching based on the stateless flow table to figure out what actions need to deal with the packet and update the connection state in CT action and recirculate back to match based on the new connection state. Connection track have to rely on recirculation based on the current design. And we have set up a test case trying to figure out how much performance impact the recirculation action has. We do the test by sending network traffic from VM to VM, prepare two VMs of the same size, and host them on the same node. Modify the flow rule to make one VM bypass connection tracking table. Sending out the traffic from these two VMs separately, touch it to the same VM node. From the testing result, we see almost 50% performance degradation. Considering the hardware offloading support, once the packet gets recirculated in software, the behavior of recirculating is just like jumping to another table to continue doing the action, which will require extra resources to support multi-table in hardware, and mapping the RT flow chain to hardware pipeline. Otherwise, the performance will also degrade if we do recirculation on the hardware. Tackle with these two challenges, we propose a new design to support connection tracking. The motivation of our new design is quite straightforward. We hope we can get higher performance in software data paths and simplify the hardware offloading support. We may also benefit from a simple hardware offloading support design, both from performance and cost. On the other hand, the new design should try to be transparent to the control plane and keep the control plane programmable. Up to the control plane to decide whether or not to enable the new logic, and the new design should be a modular design, which can support fallback to the old one. This picture shows an overview of our new design. We introduce a new action named SG, short for Security Group. Provide same function with CT action, also support connection tracking, but with different semantic. And also, we introduce a new fast path cache named SST, short for Stateful Session Table, which will maintain the connection status for each received packet. After doing the path and the metadata extract, it will first go through the SST cache. Once hit, it will directly execute the action list, include updating the connection status and as well as the per-connection statics. Once missed, which means it's a new connection, it will fall back to go through the legacy processing procedure. During execute the SG action, it will create a new connection and insert it to the SST table. So the whole design has changed to connection-oriented. Here we give a simple example to show the different semantic between the CT action and the SG action. Considering insert OpenFlow rule to implement a stateful firewall, which only allows initiative connects from port 1 to port 2, but refuses the initiative connects from port 2 to port 1. The key point to support this function is to find a way to tell the difference between the SYN-ACK flag reply packet sending from port 2 to port 1 and the initiative connect SYN flag packet. With CT action, this job is left to the control plane. Control plane have to specify the CT state in the matching field and specify what action needs to be done based on the different connection status. Thus, we need to insert at least 5 OpenFlow rules. But with SG action, the control plane will need just 2 flow rules, and the semantic is quite straightforward. The meaning of the rule is just directly define, allow traffic sending from port 1 to port 2, and denying traffic sending from port 2 to port 1, which is much more closer to the natural language. SG action will do a translation in the data plane. Allow and deny in fact is not a concrete action that can be executed. They will be translated into pass or drop separately based on the connection status. For allow, no matter the connection exists or not, it will translate into pass, and the packet can continue to do the later actions. For deny, it depends on the connection status. In case of the connection exists, then it's a passive connection. The deny will translate to pass also. And once the connection does not exist, it will translate into a drop action. Thus, control plane no more needs to specify the connection state in the match field, and can put other actions together with the SG action. Datapaths will have more information on how to deal with the packet. No more need to recirculate to do the match again. Thus, multi-actions can be unified into one flow rule, and leave the SG action to the data path which will do a secondary translation based on the connection status. And now I will explain how an SST entry is created and maintained. When dealing with a newly received packet, it will upcall to the slow path, traverse each table, and generate a new datapath flow rule. The actions on the action list will be executed. When dealing with the SG action, it will first do a datapath translate based on the connection status, figure out the packet can be forwarded or not. If the action is passed, a new connection will be created and associated with the datapath flow, which contains the action info. And then the connection will be inserted into the SST cache. The datapath flow will insert into the dpcls and EMC as usual. For the following packets from the same connection, will hit the SST cache, and the actions will be directly executed. The connection status update, connection aging, as well as the per-connection statics update are all packet-driven. Will automatically update once the packet hits on the SST entry. dpcls can work as a layer 2 cache. Once hit in dpcls, it will also create a new connection and associate the flow with the connection. Thus, it will avoid too much upcall to the OpenFlow protocol slow path. Based on the new arc design, more optimizations can be done now. For example, we may unify the vXLAN decap datapath flow, and then no more recirculation on both the TX and RX direction. The datapath flow has been unified. We can merge the actions in pair, such as the push VLAN and pop VLAN actions, to simplify the action execution. And also, we may introduce a memory pool to support the session entry fast allocation and free. Use the spin lock to replace the mutex to avoid the context switch, and guarantee the session table to be accessed concurrently. And as well as we may execute the tunnel push and tunnel pop actions in batch. Based on the same testing environment and test case, we do the performance test again. By using the SG action, we got nearly 260% performance improvement compared to the CT action testing result. And we can also benefit from the SG action design when trying to offload the datapath flow to the hardware NIC. Since the flow has been unified into one flow for each connection, and the flows contains all the match field and action field information, the hardware offloading support can be simplified. It's much more easy to offload to the hardware NIC. Guys from Baidu have contributed a lot to these two new features. Currently, the SG action and the SST features is maintained on a private version named GVS. We do have plans to contribute these two features to the community. At the same time, we also want to hear the comments from the community. Any comments on this design are welcome. Feel free to contact me via email if you have interest in it. Okay, this is all my sharing. Thank you.